What's up guys, this is Massey. Welcome to another video. In this video I want to talk about vectors in 3 space. So it can be a challenge to draw a 3D graph on a 2D piece of paper, and by convention we set the x, y and z axes as shown. The negative axes are shown with broken lines, and this is called right-hand system. So as you see here, we have the x-axis, y-axis, and we have z-axis. And if you curl a finger of your right hand from the positive x-axis to the positive y-axis, your thumb will point into the direction of z-axis in positive side of it. Now let's see how to show the point. To plot the point 2, -3, and 7, start at the origin, move 2 units along the positive x-axis, and then 3 units parallel to the negative y-axis, and then 7 units parallel to the positive z-axis. It is often a good idea to plot the coordinates of the 3D point by drawing line segments illustrating their coordinate position. Now let's see this example. It says plot these points in 3D. Plot points A 2, 6, 1, B 0, 0, -6, and C 2, 2, 3, 0. And also D -1, -3, and 4. So when you have A, you need to move 2 units down on the x-axis, and then 6 units parallel to the positive y-axis, and 1 unit you go up toward z-axis, or parallel to the z-axis. Now for the second one, we have 0, 0, and -6. We just go 6 units down on z-axis. Then you have part C. Part C, we have 2, 3, and 0. So we have 2 units toward x, 3 units toward y, and since z is 0, we don't go up or down. And also after that we have -1, -3, and +4. So we go 1 unit toward x to the negative side, as you see in here, and then we go 3 units left because it's going to the negative side, and then we need to go 4 units up parallel to the positive z-axis. And part B of this question was saying, describe the location of each point. So if you want to describe it, we can say point A is an octant that is to the front right top of the origin, where all 3 coordinates are positive. Point 8 is in the octant that is to the front right top of the origin, where all 3 coordinates are positive. Point B is on negative side of z-axis, and point C is on xy plane. And also point D is the octant that is to the back left top of the origin, where the x and y coordinates are negative and z coordinate is positive. So now let's take a look to the vectors. Let vector V represents a vector in space. If V is translated so that its tail is at the origin O, then its tip will be at some point P, x1, y1, and z1. Then V is the position vector. So we have OP is going to be x1, y1, and z1. So we have toward positive x-axis by x1. We do the same thing with y-axis, y1, and z1 for the z-axis. Now let's take a look to the unit vectors. As you saw in 2D, we had I and j with magnitude 1. I is in x-axis and j is in y-axis. But right now, since we are dealing with 3D, we have also k in z-axis as well. So as in 2 dimensions, we define unit vectors along the axis. The unit vector along the x-axis is I, which is 1, 0, 0. The unit vector along the y-axis is 0, 1, 0, and the unit vector along z-axis is 0, 0, 1. So from the diagram, the definition of unit vectors can be I, j, k, all have magnitude or length of 1. So as with two vectors, 3D vectors can be written as the sum of multiples of I, j, and k. Consider vector u as a, b, c, since the position vector of u, where the coordinates are p, a, b, c, has the same magnitude and direction as u. So as you see here in this picture, the vector can be written as OP. So it means that the tail is at the origin, which is 0, 0, 0, and the other side is going to be the position point. So how to find out the magnitude of a Cartesian vector? The magnitude of the Cartesian vector, as we see it in the bottom here, is going to be square root of a squared plus b squared plus c squared. That's how you find out the magnitude of the vector in 3D. Let's see some examples. So for each vector below, sketch the position vector, write the vector in the form of ai, bj, and ck, and then find the magnitude for these two. So u equals to 3, negative 1, and 2, and v is negative 2, 0, and 1. So we can show the position here, which is 3, negative 1, and 2. So we have 3i, negative 1j, plus 2k. So it's going to be like that, and the magnitude is going to be square root of 3 squared plus negative 1 squared plus 2 squared. If you add them all, it's going to be square root of 14. So that's going to be the magnitude of the first vector. Now let's go back and see the second vector as well. Negative 2, 0, and 1. It's going to be here. That's how we show it. So since it's x is negative 2, so we are going toward negative side of x-axis, 0 for y, so we don't move on the y-axis, and positive 1 for z. So it means that we just go 1 unit up. So how do we show it? We show it as negative 2i, 0j, and 1k. And since j is 0, we don't write it. How to find out the magnitude is going to be square root of negative 2 squared plus 0 squared plus 1 squared. That's going to give us square root of 5. So let's see the next example. Here it says find collinear vectors. Part A, it says find A such that 1, 2, 3, and 2a6 are collinear. So it means that here we have 1, 2, 3, and 2a6. If they are collinear, 2a6 must be scalar multiple of 1, 2, 3. So as you see here, 2 is double the 1 and 6 is double the 3. So it means that a is 2 times 2, which is 4. Let's see the other one, part B. Find b and c such that negative 2, b and 7, and c, 6, and 21 are collinear. So now as you see here, 21 is equal to 7 times 3. So it means that c will be 3 times negative 2. So c will be negative 6. And b must be 6 divided by 3. So it's going to be 2. So we have negative 2, 2, and 7. On the other side, we're going to have negative 6, 6, and 21. So let's see the answer. So that's how we have it. It's going to be, c is going to be negative 6, and b is going to be 2. Now let's see vector addition. It is very similar to 2D, but here we have one more component. For two vectors u, which contains u1, u2, u3, and v, v1, v2, v3, u plus v is going to be u1 plus v1, u2 plus v2, u3 plus v3. Then vector subtraction. So u is u1, u2, u3, v is v1, v2, v3. So u minus v is going to be u1 minus v1, u2 minus v2, u3 minus v3. So sometimes we have 2 points and we need to find a vector in between. So when we have points p1 and p2, p1 is x1, y1, z1, and p2, x2, y2, and z2. So vector p1, p2 is going to be x2 minus x1, y2 minus y1, z2 minus z1. So what is going to be the magnitude of this vector is going to be square root of x2 minus x1 squared, y2 minus y1 squared plus z2 minus z1 squared. Let's see an example. Interpret Cartesian vectors. Given the points A is 3, 6, and -1, and B, -1, 0, and 5, express AB as an ordered triple, then write AB in terms of ijk. Part B, determine the magnitude of AB, and part C, determine the unit vector in the direction of AB. So AB is going to be -1 minus 3, which is going to be -4, 0 minus 6, which is going to be -6, and 5 minus -1, which is going to be +6. So as you see here, it's going to be -4, -6, and 6. Or we can say -4i, -6j, and 6k. How to find the magnitude is going to be square root of -4 squared plus -6 squared plus 6 squared. For example, from example 3, on page 380 of your book, a unit vector in the direction of AB is 1 over magnitude of AB times AB. So we can do the same thing for A when we want to have it in terms of unit vector. Why? Because in part C it says determine the unit vector. So we need to divide it by the magnitude of that vector. So we already found the magnitude in the previous slide, which is square root of 88. So we need to divide each component by divide each component by square root of 88. So it's going to be -4 divided by square root of 88, -6 divided by square root of 88, and 6 divided by square root of 88. And when you simplify it, it's going to be -2 over square root of 22, -3 over square root of 22, and +3 divided by square root of 22.